In this video, we're going to learn on how to derive the equation of the sinusoidal wave function. So the wave equation is given by the following equation. Y equals to a the sine of kx minus angular velocity multiplied by t. So we want to derive this equation. So sometimes visualizing some information might be a little bit complicated when dealing with physics problems. So for us, in order to simply solve this problem, let us look at the sine wave as our reference frame. So let me say this will be our sine wave, and then this one will represent the y, and in the x-axis let us have our time. And then the sine wave will start from 0 going up down, and finally go back to the point where y is equals to 0, like this. So remember, we have some basic terms that we need to familiarize ourselves before deriving this equation. We have this point over here. So this point is our crest. This is the crest. So when we talk about the crest, it's the point at which the displacement of the element from its normal position is the highest. As you can see, this point is the highest from the normal position. And then going down, we go back to 0, and then in the negative y direction, and then this sine wave, it reach another peak value. This is another peak value. This was the first peak value as our crest. So this one is the trough. So and then when we talk about the trough, so the trough is the point at which the displacement of the element from its normal position is the lowest. As you can see, this side is the lowest because this side here is positive, and then going down below 0, the numbers become less, up to infinite, like that. So this point is the lowest. And then when we check our wave as it moves back to this point, you can see that we have now formed a one complete sine wave from this point to this point. So this distance over there is our wavelength. All right, so this is our wavelength. So the wavelength is the distance for one complete wave. Then we can also look at this point. This is also another crest. So when we move from this point to this point, from one crest to another crest, you can also have what? The wavelength. So we can also define the wavelength as the distance between successive crests, because this is also a crest. All right, so when you have this information, I think you can also look at some terms. Remember, moving this up to this point to this point here, we can see that we have formed a one complete wave, and then during the formation of that one complete wave, we have said that the wave have now gone over a certain what period. Then we have to define the term period. So when we talk about the period, it's the time interval to make one complete sine wave. So every time we make a one complete sine wave, we are going to have our period. So from this point to this point, we're also going to have another period. So the period, the time taken to make this wave from here to here, has to be the same as the time taken to make what? The second wave from this point to this other point over there. All right. Now, just because you now understand the meaning of the period, you also have to know this other term called the frequency. When we talk about the frequency, this is the number of complete sine waves that are formed in 1 second. So in 1 second, there will be a certain number of complete sine waves that are going to be formed. So now, when you check from this point going to the right, you can see that the motion is now repeating. It's now repeating. So this motion is sinusoidal. Because it is now sinusoidal, we expect the wave function to be given by the following equation. At x and y is given by t, must be given by the following equation: a the sine of ax. And then a is the amplitude, and then this variable a over there, this is our constant to be determined. So this is our variable of interest. All right. So from now going down, we have to consider the point where t is equals to 0. So once we have that point of t equals to 0, we want to make a point such that the displacement will give us a 0. Then if t is equals to 0, this is the point there, t equals to 0. And then going down, it means we'll have the following: y equals to x, and then t is a 0. This is what we have: a sine of a, then x will be what? Will be 0. All right. So this is what we have for now. So because we have a 0 here, 0 multiplied by a, we are going to have what? The sine of 0. And the sine of 0 is nothing but a 0 like that. So this equation can be generalized in this form. Because we have our x here as a 0, then the value of y that we get is also a 0. This is a the sine of a dot 0 equals to 0. So this is our first point where the displacement is a 0. So for now, we want to look at another point where we will find our displacement as 0. Then check this over here. When we move from this point to this point, describing the motion now in radians, this is pi. And then this one over here is pi over 2. And then this point over there, and this is 3 pi over 2. And then at 360, we have our 2 pi. You get that? So because we want to describe this motion here in terms of a, because we have the constant of interest at this point, which is this one. And then when we check from this point to this point, we have a pi over here. And then from this point to this point is our 2 pi. Therefore, we can see that at this point, the value of y is 0. And again at this point, the value of y is also equals to 0. But solving it in terms of a, we can simply say that the second point where x or the value of y will be 0 can be taken as this point. From this point to this point over there, divided by 2. Because once we divide this side by 2, we are going back to this point of 180 or pi in radians. Then let us now solve it in this way. So the second point, when x is lambda, this is lambda over 2, the value of y has to be equals to 0. This point from here to here divided by 2, we go back to this point of pi in radians. All right. So now let us try to fit in this information into the equation. We are saying that when x is pi over 2, the value of y has to be equals to 0. Then we'll have ax, a sine of a, and then this is x. X is lambda over 2, like this. What we have as a total will give us a 0. But bear in mind that this information which we have can be true if and only if this angle is equals to pi. because when this angle is equals to pi, it will come to this point. The sine of pi is nothing but 0. So let me write this here for the sake of space. And then a lambda over 2 has to be equals to pi. So anything other than that, this information here cannot be true. So if this is equals to pi, we can make a the subject of the formula so that we can solve this information. A will be given by 2 pi over lambda. So it follows that in space of a, we can now have 2 pi over lambda. So now this is what we have. Y at point x and t, and then t will be 0. This will be given by a the sine of a. Therefore now in space of a, we are going to have the following part, this one. So this will be 2 pi over lambda. And then in space of x, we can have x like this. So this is our equation. Y goes to x, so that y can be equals to 0. We have a the sine of 2 pi over lambda is multiplied by x. So how about if we look at this part only. So let me throw this part over here. And then let me say now from this point to this point is x. So and then I want to find the wave function at any point, because this one is when we have these points. So the wave function of a sinusoidal sine wave at any point, let me choose this point, not directly at this point was to x. So let me choose this point somewhere over there. So let me say now this point is point P. And then this wave is moving to the right. Let's say that is moving to the right. Then if we know the velocity of this wave and directly knowing also the wavelength, the lambda of this wave to the right, then we can directly find the position or the displacement of this wave from this point over here up to this point, which corresponds to this line. So if we want to find this point from here up to this point, this is nothing but the total displacement from here to here. Then we subtract the displacement moved by this wave from this point, then up to this point. Because if we have the velocity and the wavelength, remember, velocity is the rate of change of displacement over t, which means that if we multiply the velocity and the time, if we know the time and the time, therefore we can find what the distance moved by this wavelength from here up to this point. So this will be v multiplied by t. So now x will be represented by nothing but by everything which we have over here. So let us have the following information. Y equals to x at a certain time t must be given by a the sine of 2 pi over lambda. Then now in space of x, we are going to have the following information. So I will have x minus vt like this. And then from what we have here, remember we have said that velocity is the rate of change of displacement. So when we talk about the sine wave, we can relate the displacement with the wavelength, because the distance is given by the wavelength, and then the time can be related with the period like this. Just because now we have the following information, in space of v, we can have this information over here. All right, so let us now plug it in. Now we have a the sine of 2 pi over lambda x minus, then in space of v, we're going to have lambda over t, this multiplied by t. And then you can simply multiply the lambda inside. So if we multiply the lambda inside, this is what we are going to have. This is a the sine of 2 pi. So multiplying the lambda inside, we'll have x over lambda minus, this is t. Then multiplying the lambda inside, this lambda will cancel this lambda, and then t over the period will remain. Then take note that this equation that we've just formed right now, this is the periodic nature of the wave function. And then the periodic nature of the wave function at any point is the same. It does not change. We are going to show that anytime soon from now. So now, because we have the following question, let us multiply this 2 pi inside. Then I will use the space y, x, and t equal to the a sine of, then multiplying the 2 pi inside, we will have 2 pi x over lambda minus 2 pi t over t. Remember, 2 pi over lambda is nothing but this value k, and 2 pi over t is the angular velocity. So which follows that from what we have here, we can now represent 2 pi over lambda in terms of k. So this will be kx minus 2 pi over the period. Then this is what our angular velocity and multiplied by t. So this equation can be generalized in this form without having x and t in most of the cases. So this equation which we have here, it is the equation which we had to derive or prove. So just because now we have proved the equation, we need to show some very simple illustration about the nature of this periodic wave function, this one over here. Then for the sake of space, let me try to find enough space so that I can write the information properly. So we have the periodic nature of the wave equation y x t, which is given by a the sine of 2 pi. We have x over lambda is minus t over t is given in this form. So this is when we have the value of x and y at t, then at any time and at any position. So let us now say we consider the value of x at x plus lambda like this, and the value of y to be at t plus the period. So we want to show that is the same at any time and at any position. So let us show this. Then in space of x, we are going to substitute what we have here. And then now in space of t, we are going to substitute what we have here. All right. So it means that we will have a the sine of 2 pi. Then in space of x, we have x plus lambda is divided by lambda minus, then in space of t, then we'll have t plus, because of the negative, this must be negative lambda, all this is divided by this is t, not lambda, this is t, the period, all this divided by t, then close bracket. Then you can see that this lambda will divide both the x and this other lambda. Then as a result, we'll have the following outcomes. Then 2 pi, then x over lambda, then lambda divided by lambda, this is 1, minus, then divide both sides by the period, then we'll have t over t minus t divided by t, this is minus 1. Then you can see that we have a, the sine of 2 pi, then x over lambda, then we have 1 minus 1, which is 0. What remains is t over t. You can see that this equation at any time, at any position, is the same as what we have here. So we can also try the following. Then at x equals to x plus 2 lambda, and then at y equals to t plus 2t. This will be given by a, the sine of 2 pi. Then in space of x, we put in x plus 2 lambda. This is divided by the lambda. Then minus, in space of t, then we'll have t plus, because we have the negative, this negative will affect this sign to be negative because it was positive. Then we'll have minus 2 period, this is divided by the period, then close the bracket. Then as a result, we'll obtain the following. Then 2 pi, because lambda will divide both the x and the 2 lambda, therefore inside we'll finally have x divided by lambda plus, when we divide 2 lambda by lambda, lambda will cancel lambda, then 2 will remain, then minus, and then we divide by the period both sides, you will have the t over the period minus, when you divide minus 2t divided by t, and then this 2 will cancel t, and minus 2 will remain. Then finally you have the following: 2 pi, then x over lambda, 2 minus 2 is a 0, then you have t over t like this. Then now you can see that the periodic nature of the wave function at any time and at any position is the same. So this all you have to show to prove that this periodic nature of the wave function is the same at any time, at any period, and at any position. So if you find this video very useful, don't forget to subscribe and like this video so that every time I post a new video, it will be sent straight direct to you. Thank you.